Okay, so welcome to the midterm 2 solutions. And what I'm going to do is, work through the problems and, try to explain what the thinking process is. And as a result, the solutions are not going to be quite as concise as what they would be if I typed them, but I hope they'll be more helpful. So let's start with the exam. So the first problem, there's a recursively defined function. So it's defined for f of 1 as 1. And f of k plus 1 is defined in terms of f of k as the square root of 1 plus f of k. And the goal is to show that f of n is irrational for all n greater than or equal to 2. So f of 2 in this case is just square root of 1 plus 1, which is square root of 2, which we know this is irrational. Goal is to show that the rest of them are also irrational by induction. So before you start a proof by induction, you have to identify what the predicate is. You need a predicate indexed by positive integers. So let's do that. So let P of n be the predicate. And in this case, well, it's fairly clear what the predicate should be. I just want to show that the integer is irrational, that f of the integer is irrational. So f of n is irrational. Okay? And a proof by induction has, two ingredients. It has a basis step and an inductive step. So the basis step is the bottom of the ladder. And in this case, the bottom of the ladder is 2, not 1, because we want to show f of 1 is actually not irrational. So P of 2 says square root 2 is irrational, which is true, or which in the question it says you're allowed to assume that. Okay, so the basis step was sort of given to you. And the inductive step is where you have to do the work. Remember, the inductive step has a fixed format. So you start by assuming k is some integer greater than or equal to 2, some arbitrary integer. And then you assume the inductive hypothesis. So assume P of k is true. And just to be clear, let's write down what the goal is. So our goal is to show P of k plus 1. Okay, so this is where the recursive definition comes in handy. P of k plus 1 is a statement about the number. So f of k plus 1 is, so let's just write this down. F of k plus 1 is square root of 1 plus f of k. And we want to show this is irrational. Okay. So here, you might pause for a moment and think, well, how am I going to show a number is irrational? Well, okay, let me just write a comment. Let's just recall what the definition of rational is. Recall, number x, real number, is rational if there exist integers p and q such that x is equal to p over q. Okay? So it's a fraction. That's what a rational number is. And so an irrational number is a number for which this doesn't exist. Okay? And it's not so easy to prove that things don't exist, okay, because there's nothing to really put on the table. So just as we did with square root 2, we're going to approach this by proof by contradiction. So assume, for the sake of contradiction, that it's rational. This is the opposite of what we want to prove, right? Well, now the nice thing is that being rational puts something on the table, puts this fraction on the table. Okay, so thus there exist integers p and q is not equal to 0, such that f of k plus 1 is equal to p over q. Okay? And now, we want to show this is a problem. And we want to use the fact that we know that f of k is not that f of k is not rational. And now we're going to use the relationship between f of k plus 1 and f of k. So therefore, square root 1 plus f of k equals p over q. Right? That's the definition of f of k plus 1. And if you square both sides, you get that 1 plus f of k is p squared over q squared. Okay? And now you can see that this is a problem. If you rearrange this, this means that f of k equals p squared over q squared minus 1, which is p squared minus q squared over q squared. And why is this a problem? Well, p is an integer, q is an integer. So p squared minus q squared is an integer, and q squared is an integer, which is absurd since by the inductive hypothesis, f of k is irrational. Okay, so that completes the proof. The reason it's a little tricky is that inside the inductive step, you have to use a little proof by contradiction. But notice how the recursive definition, fit in beautifully into this proof. It allowed us to express f of k plus 1 in terms of f of k, and thereby use the induction hypothesis. Okay, on to number 2. So this question asks which amounts of money can be made using an unlimited supply of $2 bills and $5 bills. Formulate a conjecture and prove it. Okay, so there are two things you need to do. One is you need to formulate a conjecture first. And the best way to do this is just play with some examples, right? So what amounts of money can you make with $2 bills? Well, you can make $2, you can make $4, you can make $6, you can make any even amount. That's certainly true, because any even amount is divisible by 2. What else can you do? You can make $5. You can make any multiple of 5, 10, 15, etc. So these are just observations that'll help me decide what the conjecture is. So what's the first number that you can't make? Well, you can't make 3. Okay. What else? You can make 4, you can make 5. Can you make 6? You can make 6. What about 7? Well, 7's not even, but it's bigger than 5, so you can subtract 5 from it, and then you get 2. Okay, so 7's okay. 8's even. What about 9? Well, again, you can subtract 5 from it and get a positive number because bigger than 5, and you get 4. So that also works. But now, we see a pattern here, right? If you take an odd number and subtract 5 from it, you get an even number. So maybe 3 is the only one, right? If you take any odd number bigger than 5 and subtract 5 from it, you get an even number, right? So odd number bigger than 5 minus 5 equals positive even number. So you can actually make any odd number bigger than 5. And so maybe the only number you can't make is 3. And you can't make 1, right? Can't make 1. Because it's less than both 2 and 5. So let's make this a conjecture. Every positive integer amount, you can't make 50 cents, except $1 and $3 can be made with $2 and $5 bills. Okay? And now that I made the conjecture, I have to prove the conjecture. And the proof, actually the main idea of the proof is what I wrote here, this observation. that, well, if it's even, you're done. And if it's odd, you can subtract 5 and get an even number, in which case you're done. So what's the proof technique that allows us to do this? Well, it's induction, because this observation, really what it's doing is telling me I can solve a bigger problem, assuming I can solve a smaller one. So one way to do it would be induction. But actually in this case, it's even simpler. Okay, so now let's prove this conjecture. There are many ways to write a proof. For example, there's a direct way to turn the proof in the previous page, the idea on the previous page into a proof. But let's just do it by strong induction. It's a systematic way to do it. So to do induction, you need a predicate, and the appropriate predicate here is indexed by an integer n, is that n dollars can be made from $2 and $5 bills. Okay, and our goal is to show that this is true for a certain subset of the integers, right? It's true for 2, true for 4, true for 5, and then true for all n after 5 that are at least 6, right? That was our conjecture. So let's do it by induction. So what's the basis step? In the basis step, I'm going to handle all the exceptional cases, which is these 3 numbers out in front. So observe that P of 2, P of 4 are true, well, because 2 and 4 are even. So one $2 bill and two $2 bills work. And P of 5 is trivially true. Okay, so these are the base cases. And now let's do the inductive step. So we're going to do this by strong induction. So assume everything up to P of k is true. So P of 2, P of 4, P of 5, all the way up to P of k are true. Okay, and of course assume k is some number that's at least 5. So now our goal is to show that P of k plus 1 is true. So what we have to do is relate P of k plus 1 to P of k or something smaller. So the observation is that, well, if you have some number k plus 1 and k is at least 5, then k plus 1 is at least 6. So what that means is if you subtract 2 from it, you're going to get a number that's at least 4, right? So observe that k plus 1 equals 2 plus k minus 1, and k minus 1 is at least 4. Why? Because k is at least 5, right? And now the point is, by the inductive hypothesis, P of k minus 1 has to be true, okay, because it's at least 4. So what that means is that there's a way to write k minus $1 in $2 and $5 bills. But now we're done, right? Because, okay, so there is a way to write k minus $1 in $2 and $5 bills. And now we're done because if we add another $2 bill, we get k plus 1. Okay, and this completes the induction. Okay, so the only slightly tricky thing here was deciding what the base case should be. So if you don't do the base case carefully, you can get in trouble. So for example, or if you've done something like try to subtract 5, then you would have had to have a different base case. So because there were these exceptions, $1 and $3, you had to think carefully what the base case should be. But that's basically it. Okay, on to number 3. This is a counting problem, and the question is how many poker hands contain one ace, exactly one ace, no king, and at least one heart. Okay, so there are these 3 constraints. There are 52 cards. I have to choose 5 cards with these properties. So the first thing to observe about this is that this exactly one heart constraint is sort of annoying, right? It could be 1 heart, it could be 2 hearts, it could be 3 hearts, it could be 4 hearts, it could be 5 hearts. And this is, there are many cases here if we want to add all these things up. So it might be easier to just count all the hands that only satisfy the first 2 constraints, okay, all of them, and then throw away the ones that have 0 hearts, right? So by the sum rule, so the number of hands we're interested in is equal to number of hands with 1 ace and no king, no constraint on the hearts, minus the number of hands with 1 ace, no king, and no hearts. Okay? So let's call these quantities A and B, and let's, count them. So let's do A first. So again, how do you count something? Well, you define a process that constructs the object you want to count. So consider the process. So how do you construct a hand with 1 ace and no king? Well, it has to have an ace. So first you choose the ace. So choose 1 ace. And then you have to choose the rest of the cards. So you have to choose 4 more cards. But then they can't just be anything, right? So they can't be kings because there are no kings. And they can't be aces because there shouldn't be any more aces. So no kings or aces. And now how many ways are there to do these steps? Well, how many ways are there to choose 1 ace? There are 4 aces in a deck, so there are 4 ways. And how many ways are there to choose 4 cards out of the remaining cards with these constraints? Well, there are 4 kings and 4 aces. You can't use those. So 52 minus 8 is the total number of cards you have left to work with. That's 44. And you have to choose 4 out of those. The order doesn't matter. So you have 44, choose 4. Okay. So therefore, by the product rule, A is equal to 4 times 44, choose 4. Okay. Okay, let's now do the other count, B, which is the number of cards with no king, exactly 1 ace, and no hearts. So here what's going to happen is, again, we have a process. First step is choose 1 ace. There are 4 ways to do that. Second step is choose 4 cards. But now, okay. Actually, I'm sorry, I've already made a mistake. We're not allowed to choose hearts in this situation, right? So when you choose the 1 ace, there's actually only 3 possibilities. The ace of hearts is gone. Okay, so you got to be careful here. And now in the second step, you have to choose 4 more cards, and no king, ace, or heart is allowed. Okay. And this, you have to be a little bit careful. How many cards do you have left to work with? Well, you have 52 cards total, and 13 of those are hearts. So you have minus 13 hearts. That leaves you with 39 cards. And now you're not allowed to choose kings and aces, right? Well, there are 4 kings and 4 aces in the deck, but because you already threw away the hearts, there are actually only 3 kings and 3 aces left in the deck. So you have to throw away all the remaining kings and remaining aces. And you get 39 minus 6, you get 33 cards. Okay? So you have 33 cards left to choose from. And the total number of ways of choosing 4 things out of 33 is 33 choose 4. Okay? So again, by the product rule, the total number of ways is 3 times 33 choose 4. So the answer is 4 times 44 choose 4 minus 3 times 33 choose 4. And I'm not going to ask you to simplify these huge numbers in the exam. You can just leave them in this form and that's fine. Okay, on to number 4. This is quite a tricky one. It's sort of a tricky pigeonhole problem. And so what you're given is you're given an integer n that's odd, positive, and a function f which is a bijection from 1 through n to itself. Okay, and the goal is to show that this number 1 minus f of 1 times 2 minus f of 2 all the way up to n minus f of n is even. Okay. Now the hint here is really important. If I just showed you this problem, it wouldn't probably be obvious to you that you would have to use a pigeonhole problem, the pigeonhole principle. But let's see what we can do. So the first observation is that, well, to show that a number is even, so this number is a product of a bunch of numbers, right? To show that it's even, I just need to show that one of these is even, right? So observe, it's sufficient to show there exists some I such that I minus f of I is even. Why? Because if you multiply an even number by any other number, you get another even number. Okay, it's enough to show one of the factors even. Okay, so rather than just write out the completed proof for you, let me try to build some intuition for what's going on. Let's draw a picture, right? So here you have the numbers 1 through n. And then you have some function that's mapping them again to the numbers 1 through n in some way. The important thing is the function's a bijection. So it's 1 to 1 and on to. Okay, it's a permutation. And what you're interested in is this difference, right? Along each arrow, you're interested in I minus f of I. You want to show that one of these things has to be even. So here you want to use again this fact that, I mean, this number is a difference, right? When is a difference of two numbers even? Well, it's even if they're both odd or if they're both even, right? So observe, if I and f of I are both odd, then I minus f of I is even. So if you can find an odd number that gets mapped to an odd number here, you're done. Okay, so now my goal is to show that there's some odd number that gets mapped to another odd number. Let me now define some sets. So let O be the set of all integers, between 1 and n, and k is odd. Okay. Now my claim is there exists some integer I in the set of odds such that f of I is also in odd, right? And if I can do that, I'll be done, because then I minus f of I will be even. What's the proof? Well, the proof is going to be by contradiction. So assume not. And what does that mean? Well, that means that everybody in the set of odd integers gets mapped to an even integer. So assume the set f of O is contained in the set K such that K is even. Okay. Okay. Now, why should this be a problem? So there's one thing in this question, in the problem, in the statement of the problem that I haven't used, which is that n is odd. Okay. And whenever you see a question and there's something that's given to you and you don't use it, you should be thinking about, where am I going to use this? So this is a place where this is going to come in handy. I'm going to observe. Okay, so call the set of even integers E. Observe that the set of odd integers between 1 and n has one more integer than the number of even integers between 1 and n, since n is odd. Okay, if you take an odd number, then if you look at the numbers 1 through n, both the endpoints are odd, and the numbers in between are even, but there's one more endpoint. So there are more odd numbers than even numbers. So thus, f is mapping a set of size, okay, evens plus 1 into a set of size evens, right? Thus, f maps e plus 1 elements to e elements. Okay, but now this is where you apply Pigeonhole, right? So by Pigeonhole, there must be some number, let's call it j and e, such that well, the preimage of this set has more than one element. Okay, so there must be some box that has more than one pigeon. Okay, but now this is impossible because the function is a bijection. Okay, so what does that mean? Well, thus there is some I such that f of I minus I is even. So the product, or I minus f of I, is even, as desired. Okay, so I mean, okay, this was the hardest problem on the exam, but roughly what it's saying is you start with your numbers like this. Let's circle the ones that are odd. Okay. Now the point is there's one more odd than even. And so if this thing is a bijection, if all the odds get mapped to evens, then there has to be a collision somewhere by Pigeonhole. Okay. And this is not possible. This is not possible because it's a bijection. So what that means is there must be some odd number that gets mapped to an odd number. This dotted line, and that's the one you want. That shows that the product is even. Okay. Okay, now we're going to solve number 5, which is a probability question. And so it says we do this experiment where first you choose a bag, and the bags are called A or B, and then choose a ball from the bag. And the bags have different distribution numbers and distributions of balls. So bag A has 3 red balls, 4 blue, and 1 green. And bag B has 1 red, 10 blue, and 1 green. And so the question is, what is the probability that you draw a blue ball in this experiment? That's the first one. And the second one is, what's the probability that you drew from bag A given that you draw a blue ball? Okay. So before we can compute any probabilities, let's just make everything clear. So in order to use math, we have to explicitly define probability space. So the probability space here is it's going to have 6 points, which I'm going to call A red, A blue, A green. So I mean there's 2 things in the experiment, right? There's which bag and which color. So I'm just going to make all combinations of these things. B red, B blue, and B green. So the probabilities, so the sample space contains 6 points, but not all these things are equally likely, right? So we have to assign probabilities, and instead of, the probabilities aren't just given to us in this case. What is given to us is the following probabilities of certain events. So what events do we know about? Well, one event is that bag A is chosen. One event is that bag B is chosen. So these are all subsets of the sample space. One event is that a blue ball is chosen. One event is that a green ball is chosen. And one event is that a red ball is chosen. Okay, so each of these refers to the subset of the sample space where the appropriate bag or color ball is chosen. And then what we're given about this is a bunch of probabilities. So we're given that the probability of bag A is a half, and the probability of bag B is a half. Right? In the problem it says we choose one uniformly at random with equal probability. So this is what we're given. And then the other thing we're given, actually, if you think about it, is a bunch of conditional probabilities, right? So what we know is once you choose a bag, let's say you choose bag A, then it's very easy to calculate the probabilities of choosing balls of different colors, right? So the probability of picking a red ball, given that you chose bag A, is, well, okay, so there are 3 red balls in bag A. And what's the total number of balls in bag A? It's 3 plus 4 plus 1. So it's going to be 3 over 8. And similarly, the probability of picking a blue ball given bag A is going to be 4 over 8, which is a half. And then the probability of picking a green ball given bag A is 1 over 8. Okay. So this is what we're given. And then we're given a similar thing for bag B. So the probability of red given bag B is 1 over 12. There are 12 balls in bag B. Okay, so that's everything we're given, written in conditional probabilities. We're not actually going to end up using all of these, but I just wrote them for completeness. I mean, maybe when you solve this problem, you only write down the ones that you need, but okay. Okay, so now we're in a position to use, the theorems of probability to calculate the probabilities of the events we're interested in given these probabilities, right? So the first part is what's the probability of seeing blue? Well, I don't know that, but I know the conditional probability of blue given bag A or given bag B. So what I'm going to do is use the law of total probability to break this into these conditional probabilities. So it's the probability of seeing blue given bag A times the probability of bag A plus the probability of seeing blue given bag B times the probability of bag B. This is by law of total probability. Why can we apply this law? Well, because the probability of bag A plus the probability of bag B equals 1, and these events are disjoint. Okay? Okay, and now all these things I actually know, so I can just plug them in. So probability of blue given bag A is a half, probability of bag A is half, plus the probability of blue given bag B is 10 by 12, times the probability of bag B is a half. So what this ends up being is just, well, okay, let's just do the calculation. It ends up being a quarter plus 10 by 12 is 5 by 6, so you just get 5 by 12, which is 8 by 12. Okay, is that right? Yeah, which is 3/4. So you have a 3/4 chance of seeing a blue ball in this experiment. Okay, and what we use is law of total probability. Okay, so in the second part, we are asked to find the probability that we chose bag A given that the ball that we drew is blue. Okay, so suppose you do this experiment, but then you forgot which bag you took it from, but you can see that it's blue. So what's the chance that it came from bag A? Well, this is not something we know how to compute, but we do know how to compute the probability of getting a blue ball given that you chose bag A. And so, the natural thing to use here is Bayes' rule, which allows you to flip the conditional probability. So Bayes' rule says that this is the probability of getting a blue ball given that you're in bag A times the probability of bag A divided by the probability of getting a blue ball total. And these are all numbers that we know, right? So that we wrote a couple of slides ago. The probability of getting blue if you're in bag A is a half. Probability of bag A is a half. And the probability of getting blue in the experiment overall is the first part of the question, which we calculated. And the answer to that was 3/4. So if you put these together, you get that the probability that it was bag A is 3/16. And this intuitively makes sense. You're less likely to have got it from bag A because bag A has a smaller fraction of blue balls than bag B. Almost all the balls in bag B are blue. So if you got a blue one, it was probably from bag B. But if you want the actual probability, you have to use Bayes' rule like this. Okay, one more probability question, number 6. What it says is that everyone in a class of 260 people, such as our class, is assigned a random birthday in the set 1 through 365. Let's assume there are 365 days in the year. And there's a definition here. So call an unordered pair of people magical if they have the same birthday. So by unordered, I mean that, if you have two people, Alice and Bob, that's the same as Bob and Alice. And the question is, what is the expected number? of magical pairs. Okay, so again, right now this is written in English. To use probability, we have to define a sample space. So let's do that. So, well, the sample space here is going to be the set of all sequences of birthdays of 260 birthdays, right? There are 260 people, and each birthday comes from the set 1 through 365. Okay, so in other words, it's actually just the set 1 through 365 raised to the 260. It's all 260 tuples of numbers that come from 1 through 365. And there are no constraints. There can be repetitions. Of course, 2 people can have the same birthday, 3 people can have the same birthday, and so on. So that's all there is to the sample space. And I'm interested in computing an expected number of something, of magical pairs. So let me define a random variable x. So remember, x is a function on the sample space. So x of b1 up to b260 is the number of unordered pairs of people in this set of 260 who have the same birthday. So formally, okay, so intuitively, this is the number of magical pairs. And a magical pair is 2 people who have the same birthday. So it's going to be the cardinality of the set of all let's say I pairs ij such that pi equals bj, okay, and I is less than j. So the reason I put I is less than j is because I don't want to count ij and then ji, right? And I also don't want to count somebody as being a magical pair if they have the same birthday as themselves. I want I to be different from j. Okay, so formally, given a tuple b1 through b260, number of magical pairs is exactly this. It's a number of pairs I comma j such that bi equals bj. Okay, and of course I and j are in the set 1 to 260. And what we have to do is compute the expected value of this random variable. Okay, so again, so recall that the expectation of a random variable is the sum over all points in the sample space of the probability of that point times the random variable evaluated at that point. But the point is, the sample space is huge. This function looks kind of complicated. It's counting. It's looking at all possible pairs of coordinates. So it looks like a complicated function. So the idea is to decompose it as a sum of simple functions, of simple random variables. Where simple means, it shouldn't depend on everybody in some sort of complicated way. Maybe it should only depend on 1 or 2 people. So the right thing to do here is to define a random variable for each pair of people in the class, okay? So define for every pair ij such that I is less than j, a random variable xij, which is going to be 1 if bi equals bj, if they have the same birthday, and 0 otherwise. Okay. So implicitly, what I mean by this is that xij is a function of b1 up to b260. Okay. All right, and I and j, of course, have to be between 1 and 260. Okay, so maybe this is redundant. I can just write it like this. Okay. And now the upshot is that that the total number of magical pairs is just equal to the sum of these. So it's equal to the, it's equal to x12 plus x13 all the way to x1260 okay, plus x23 plus x24 all the way to, just put commas here to make it clearer. Okay, all the way to x2, 260, and so on. In summation notation, just sum over all I less than j of xij. Okay. And so now the point is that by linearity of expectation, I have that the expectation of the number of magical pairs is equal to the sum over I less than j expectation of xij. So all I need to do is compute the expectation of xij. And so now I'm going to calculate this. Well, the expectation of xij is equal to the probability that bi equals bj, right? So what I really mean formally by this is that, well, it's the probability of an event. What's a subset? It's a subset of all points in the sample space such that bi equals bj, right? Xij is the indicator of this event. And now I just do my very basic counting calculation. Well, again, so all birthdays are equally likely, right? So all I need to do is count the number of points in the sample space where bi equals bj and divide it by the total number of points in the sample space. Okay, so I need the cardinality of this set bi equals bj divided by the cardinality of s. And now I'm going to go back to counting. So how do I generate a tuple of birthdays with the property that bi equals bj? Well, I choose bi. There are 365 ways to do that. That fixes bj. Okay, I don't have any choice for bj. And now there are 258 people left, and I choose all of their birthdays, and for each of them there are 365 ways, right? So what I get is I get 365 to the 259. That's the number of ways of assigning birthdays in which bi equals bj. And of course, the total number of birthdays is 365 to the 260. So it's just 1 over 365. And this is true for every pair. Okay? So this is where the gain is, right? That if I only look at two people, if I zoom in on two people, it's pretty easy to calculate the chance that they have the same birthday. There are other ways to do this. You could have done this with conditional probability, but this is the most concrete one. Okay, and now we're basically done. So since this is true for every I less than j, what I get is that the expectation of x is the number of pairs with I less than j times the expectation of one of the pairs. Let's just say x12, they all have the same expectation. Well, what's the number of pairs? Well, how many ways are there of choosing two unordered distinct objects out of 260 objects? Well, 260 choose two. And this expectation is just 1 over 365. So the answer is 260 times 259 over 2 times 365. Okay, which, let me just run it through a calculator. I don't actually know what it is. Okay, let's see if we can do some simplifications. 130 times 259 over 365. I guess we can cancel 5s. So this becomes a 26. What is this? 73. Well, okay. I'm just going to leave it like this. Okay. So anyway, in general, I'm not I'm not going to ask you to simplify your answers on the midterm. You don't have to run it through a calculator as long as you get the right expression. Okay. So the idea was just use linearity and then count the number of pairs. And for each random variable that depends on two people, it's relatively easy. Actually, okay, now I'm sort of actually curious what this number actually is. So let's just see. Wow, so it's actually 92. It's 92.24. So there are going to be about 90 pairs of people who share the same birthday in our class in expectation. Okay, last question of the exam. It's a true or false question, and it's asking if you have two random variables, is the variance of the sum always bigger than the sum of the variances? And the answer is it's actually false. I presented this in class yesterday. And the simplest example is you consider, let's say, let's just be explicit, consider the coin flip probability space, consider x to be plus one if head, minus one if tail, and y to be the opposite, minus one if head, plus one if tail. Then you see that, well, the variance of x, so what do you see? From this, it's easy that the expectation of x is 0, the expectation of y is 0. So the variance of x is just going to be the expectation of x squared, which is 1. The variance of y is going to be the expectation of y squared, which is also 1. But then what's x plus y? Well, x plus y is 0. X plus y is always 0, right? Because x is equal to minus y. So the variance of x plus y is 0. And okay, 0 is not bigger than 1 plus 1. So that's it. Good luck on the exam, and feel free to post on Piazza or email me if you have questions about any of this. And yeah.